Nothing, no sound. Huh?
Hello, Prof.
What's wrong with the microphone?
Hear us?
Oh, can you hear me?
Yeah.
Okay, all right, good. All right, it's recording, right? Yeah.
Yes.
Okay, everything's okay. Good. All right, so sorry, this is the paper this week. So they put the where the so the authors are here, right? Way down at the end in these in the macromolecules. Yeah.
Why don't you drop this?
Oh, okay. That's a good question. On projector. Yeah. Anyway, they're from China. I don't know the universities. The State Key Lab seems to be like a popular place. And I don't know these other schools. I mean, there's so many schools in China and I haven't been there. So anyway, but it looks like a pretty good paper. They have this idea of all right, so they take a magnetic particle. This is called magnetic tweezers in a magnetic field, and you can pull the chain up. So if you can covalently bond the chain to the surface, then bond it to a magnetic particle, then you can pull it up, and then you can kind of put a force on it, and then you can make this. If it's penny PAM, you can put it through the gel collapse transition. So coil to globule transition, and then you can pull it once it's a globule, and then from that information they try to get what the structure of it is, to get a cartoon of what the structure of the chain is, right? So this picture kind of says everything they want to say. The main conclusion is that there's this 31 repeat unit bead that forms, which isn't part of the Grossberg thing. So they don't explain like why it forms a 31 repeat unit bead, right? So there's a couple of problems to this. One is that they never explain like why, they never even guess why. And then the other big problem is they didn't look at the literature, like they didn't review the literature at all, so like there's a lot of papers about doing this kind of measurement. So one way you can do it is you take an AFM, which is like a cantilever, and then it's got a tip that's kind of one atom tip, and then from the deflection of the cantilever, you can get the force, right? So you can get an AFM, you can trace across the surface, and you use a laser to see the position of the cantilever. It's just a bending a beam process. Anyway, so you can take that tip and you can glue a polymer to it, or this penny PAM or DNA or something. And then you can stretch out molecule with the AFM. And the other way is you can use, so there's like, I guess, a force that light creates. So you can have a light tweezers also. So you can take a particle and kind of levitate it if you have strong enough lasers. What is it? Optical lasers. Yes, you make like an interference pattern with the two beams, and then the bead can get stuck in it. I'm not exactly sure how that works. It's something to do with Einstein, though, I think. It's something photoelastic, something or other. I don't know. Anyway, so somehow the laser beams can hold the bead. So there's three ways to do this. This magnetic way is, I think, the newest way, so it's kind of interesting in and of itself. This paper's by some guys in Oklahoma that I guess are experts at this. It's a pretty good paper. It's in Frontiers in Physics, which is one of these, I think it's kind of a pay to publish journal, like MDPS or something. Yeah, so it's like one of those journals. But basically, this is a pretty decent. I thought it looked pretty good. I learned by looking at it, so they show the magnet. So the problem with the magnet is every bead is different, right? So how do you get the force on this? And the magnetic field isn't like that easy to control. So what they do is so So the particle's small enough that it's moving by Brownian motion, like the gas atoms are hitting it, so it's vibrating thermally. So, and you can measure that if you do optical tracking of this, you have like a camera watching that, a high-speed camera, and you can get the speed of these particles moving around. You get an X, Y, and Z direction. You can get this vibration. So if you look at the data, it always has this vibration. See, that's thermal vibration from Brownian motion, right? And that thing changes. So from that vibration, he tells you how to do it here. You get delta y squared, the mean squared distance of displacement for that kind of random oscillation. From that, you can get the force basically just using, he says he has like a spring constant. So that R squared's KT divided by this horizontal stiffness of the trap, like a spring constant. And from that, this gives you a spring constant. If you know the temperature, so you need to know the temperature accurately. You need to know this vibration, which you can measure easily. Then you can get the force from that. As you increase the force, that vibration changes. So they're inverse to each other. For higher force, you get a smaller vibration. So that's kind of interesting because it's using like Brownian motion and things like we already talked about that. And then he's got the Stokes-Einstein equation, and he's got the Stokes laws in here someplace because it's a spherical bead, so you can use a 6 pi, the air's viscosity or whatever fluid it's in, and then the size, the radius of the bead. So so this goes through like kind of the mechanics of it and how you can. All right, so one advantage of this is that you can so with the AFM, so you can't twist it in a circle, right? And same with the laser, you can't really twist it around. So the big problem is like, so they do like a dip and pull measurement with AFM, so you reach in and pull up, so you can get more than one polymer. You get some short ones, some long ones. So you don't know what you're actually doing. It's a blind experiment, right? This magnet, and same with the light thing, it's kind of blind. So this measurement isn't blind because you can twirl it around, and when you twirl it around, if it's one chain, he shows in here somewhere. There, let's just show it. It's early on. If it's a one chain, it's a circle like this. So he's got dy dx. We can measure y and x with cameras, right? With the high-speed cameras. And then he spins his magnet. So he's using an electromagnet so he can spin it. Or the original ones were just used on the static magnets, Anyway, you can do it with static, or you can use electro. Anyway, somehow you can spin the magnetic field, and if it makes a circle, that means it's one chain. If it isn't, he shows in the supplemental, if it isn't one chain, then he shows what it looks like here. You get this kind of ellipsoid thing. Somewhere in here he shows it, I think. Maybe not. Maybe it's the other paper that shows it. Oh, here. So he gets this if it's more than one chain. It's strikingly different than the circle. So he knows it's one chain, so that's good. I think all this comes, you buy this machine and it tells you all this. So this isn't something he invented. And you can see the oscillator, as the force increases, the oscillations, so this is a constant force. Someplace they show change in force. You can see the oscillations change with the change in force. He's doing, oh yeah, he does that because he's trying to make it like a muscle. So he does a 2 piconewton and then switches it to 6 piconewton to say like it's got some steady tension on it when it's relaxed, and then when it's not relaxed, it's got the 6. So he goes through that transition to kind of mimic how muscles work. And he's got some AFMs of maybe that's in the supplemental. This paper uses one problem is it's like using the supplemental, you have to read the two together. You can't get it without both things. This isn't it. So the supplemental, I guess, has this business of the muscle thing. So he's got, let's see. The bottom is force. This is extension. This is X and Y. Of all these plots are done the same. That's a step thing. step 4, he does a 2 and then the 6 somewhere here, where he's kind of doing like to see what happens when it's got a tension on it and then it pulls out. Anyway, it's in here someplace. He also does some weird thing where he claims that these are the collapsed coils. That's the bottom line. And he does it, he says, like, if you just put the stuff on the surface and do an AFM, the polymer lies down and it's the thickness of the polymer layer is the same as the roughness of the surface, so you can't see it. So he does some kind of tethering process that I didn't really understand, and somehow he gets to get an image of these things. You know, so basically, I mean, let's see, that's in the paper here, the last part. So that's the other thing he does, is just straight AFM of to show images of what his coil things look like, and it starts to look like his cartoon, you know. So I mean, these micrographs can be misleading, you know, so you can't, what's that? Well, he's got a whole, they aren't DNA, it's PNPM. It's polyanisopropylachrome, so it's got like a protein, it's got a polyamide side group, yeah, and that's just a vinyl polymer on the back. It's carbon, carbon, carbon. Right, so it's got hydrogen bonding off the side. I don't know if he shows the polymer here. Might show it at the beginning. No, he doesn't show it. It's just like got this polyamide side group, and then it's a vinyl in the middle. It's carbon, carbon. So it's a lot of nuances to this. Like, so because it's a vinyl polymer, it can have tacticity. So people have looked at isotactic PNPM and syndiotactic PNPM. And I guess he's talking about atactic PNPM. I'm not sure, he never says. But they're different. They aren't the same. You know, they have different stretch characteristics. People have already done the AFM on this thing, the tip stretching thing, pretty extensively. So, and he fails to even really kind of note mostly what other people have done. So it's a little bit of a problem. At first, it looks like a really good paper, and he's got this theory that he says, well, the collapse isn't a collapse. It collapses in 3 stages. One stage is it makes beads. The second stage is like the beads can merge if they're near each other. And the third stage is something he calls stacking of the beads. Okay, so these are all things, I think at this point, I think they're figments of his imagination. Okay, so I can show you why. I mean, there's some other papers, but anyway, it's a good paper to see, to critique, actually. At first, I thought it was a good paper because it's kind of the same thing with the Grossberg. But I think it's probably a good one to see how people convince themselves of something by drawing a picture that is devoid of reality. You know, so you have, all right, first off, there's techniques where you don't actually see the structure, right? Like rheology, where so you can say like, well, the viscosity drops because the chains stretch out. But there's a big disconnect between a chain stretching out and measuring how something flows. The flow measurement is on a macroscopic scale, and the stretching of the chains is on a sub-nano scale, right? So I mean, there's a lot of things in between those two. It isn't just like, right? So anyway, it's the hierarchical structures you're talking about. So it's not so simple to just say that. It's easy to kind of understand it that way, but basically, this turns out to be kind of BS, like the whole thing he's talking about here. So anyway, it's kind of interesting though. So he's got then this thing's gonna pop, and it turns out it pops at 30, this is 7.8 nanometers. It pops, and that's like 14 nanometers and 21 nanometers. It's like pop, 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 pop. So he's going, oh yeah, of course. That's a bunch of these little collapsed spheres, right? I mean, that's kind of what's popping. So it's got to be 30, and then he says like 7.8. If it was a solid object, it's going to be 31 repeat units in it, right? So that's his number. So the magic number for this PNPM to collapse is 31 repeat units, right? So anyway, so it kind of looks convincing at first, you know, until you kind of see what's in the literature. Then he says like, how long does it take to pop? So let's see, where's his data here? So he pulls it. So his force is 6 piconewtons here. Then you have to wait. There's a certain lag time, and then it pops. There's 7.8 nanometer. And it pops again. So it's like lag times. And he finds out that there's 2 different kinds of lag times. One is a lag time for one of them to pop, and one of them is for 2 of them to disjoint from each other or something. Right. So he can map out all this stuff. So you can map out the frequency of different lifetimes for these. And he says there's two exponentials to it, one here and like one out here. Pretty noisy. I mean, it's not exactly, you can get that. Then this is the speed of the transition. So the speed of the transition, so he's got the speed of how fast this jumps. You can see the early ones are instantaneous, and then the latter one, which he says is the whole collective thing. This last one is the folding of it. Like he says, stacking of it. So he has primaries popping off, then these binaries kind of unhooking. And then the last one with this multiple steps is, he says it's unfolding or unstacking. So he says they stack. So stacking is kind of in 1D, so it's kind of hard to see what he's talking about. But basically, this thing that's going slowly, he says that's a rate, so he can get nanometers per second out of that. He can get a rate. And he's got this rate somewhere here. Nanometers per second versus the rate versus the, I don't know what J is, jump length. How big is the jump? How big is the step that it takes? So that's basically the 7.8, or else it's going to be like 7.8, 14, 21, whatever, right? So you can plot that out versus each of these discrete jumps that are happening. And then you can plot that versus the relaxation time that you got. How long did it take to get to that jump that went at that rate? And he says these are correlated. They kind of look like noise patterns, but I mean, maybe they're correlated. Anyway, he's just looking to try to get some general trends of the thing. From that, he constructs a story that's kind of coherent. So it's not poorly put together. It's just that he didn't read the literature. That's the problem. Like it's not, you could critique, like, is there anything in this, or is this just noise? But basically, I mean, it's okay what he says about it. So anyway, what else is in here? That's kind of where this paper's going, right? So what is it from this class, like, you should know, like, what do you think about polymer chains, like, right? And this is a polyelectrolyte, like it's got a side group. So let's see, what if this other paper, not them, these guys probably show this polymer. Not exactly. Oh yeah, penny pan here. Right, so it's a vinyl polymer, and it's got this basically like a protein sticking off, and there's an isopropyl stuck to the protein. So there's a carboxyl and an amine. So this group is a sheet. It's flat, right? Because there's a resonance structure between the carbonyl and that nitrogen carbon bond. So that flips back and forth. That means it has to happen on a plane. So that thing's like a card, and then there's a little propeller sticking off. This isopropyl is like a propeller that's spinning around, right? And this nitrogen, that hydrogen bonds. So you get, I mean, this German paper, so this is from Freiburg, which is like a pretty good school, German schools, there's not like one MIT in Germany, Germany, all the schools are pretty good. It's kind of different. So Freiburg's a good place for polymer stuff. It's not the best place. Mainz is the best place, but that's more of like a research institute, and this is their actual university. And then the Free University in Berlin's another. I mean, they're all good schools. Darmstadt's a good school too. So they're a lot more spread around, like more uniform quality of schools. All these. So these are all different schools, but they're all pretty good schools. So it's kind of a trustworthy group, I guess. At least we know who they are. So he's looking at PEG, polyethylene oxide. So it's, if I can just expand this guy. So PEG is like, I think I mentioned it before. So it's just polyethylene, carbon-carbon, and then oxygen in it. So it's got an ether linkage. So the ether linkage makes it can dissolve in water. It doesn't have a phase separation temperature, it just can go into water. So if you put 3 carbons here, that's polypropylene oxide, right? And you can make a copolymer that anionyically polymerized. You can get monodispersed chunks of polyethylene oxide, or it can be, it's called polyethylene glycol too. So it's the same thing, PEO, PEG. And then with polypropylene oxide, so you can change the 2 block lengths, right? So you can tune the miscibility. Polypropylene oxide is not miscible in water. Polyethylene is. So you can get micelles formed with it. So you can have like a core shell. So you can have the ethylene oxide on the outside and the propylene on the inside, make spheres and make whatever you want, rods, whatever, right? Or you can tune the miscibility in other solvents too, like ethanol. So if you tune the propylene and ethylene lengths, then you can make a gel and ethanol, and that's what hand sanitizer is, right? That's whatever goo you put on. And then it can be used for if you need to wash out your intestines, you eat polyethylene glycol. You just put it in water and lemonade, drink it, and it'll flush you out, like when you need to do a colonoscopy or something. So, and then it's biocompatible, totally non-toxic, right? So actually the non-toxicity of it has been questioned recently. So people develop allergies to polyethylene oxide. So now they're saying like shampoo that's peg free or something, right? So there's like things about, but basically you can eat it, and it doesn't do anything to you for the most part, unless you happen to have a weird allergy to it. So hope no one in here has that allergy. It's like kind of making fun of it, but anyway, so there's a lot you can do with that copolymer. You can make drug delivery with it. There's a lot of things, right? And the same with PNPM. It's like drug delivery is one of the main things they talk about. So anyway, so this guy's doing both of those. And then, all right, so then he says like, well, what's the difference? Well, the persistence length is different, so if you look at the persistence length, let's see, this is in the supplemental of this thing here. So the persistence length per oh wait, the Kuhn length, you get that? I don't know why he gives the Kuhn length for the polyethylene oxide and the persistence length for the, wait, the Kuhn length is 7 angstroms, so 0.74 nanometer. And it's not temperature dependent for the polyethylene oxide. These are experimental measurements. He also does simulations in here. And then the persistence length for the other guy is like 2.5 nanometers or 3 nanometers. Right. So basically 2 times this is a Kuhn length. So that's 6 nanometers. And his measurement when he gets 31, that's 7.8 nanometers. So 6. So the thing, I mean, so you have to look at this way, like this guy, what is he running? That's good. Lights go. You have these chunks. All right, so this guy says,
Okay.
huh? Oh, all right. Auto. So, it's okay. Oh wait, it's doing it. It's not doing it. Auto again. I'm gonna do it.
Yeah.
Is it? All right, good. All right, so this guy says 6 nanometers, 60 angstroms, pretty far. And I have another paper here by where they do a simulation. Sandia, let's see. And they get 9 to 10 monomers. So basically 20 monomers. So he's saying 31. And he's saying that each monomer is 1.54 times 2. This is what the Chinese guys do, which is like 3 3.1 or something times 20 gives you 62, the 6.2 nanometers. Right, and he's getting 7.8. Somehow he got 7.4 from the Sandia one. Anyway, I still think it's 7.4 nanometers. So anyway, there's no difference between, this is 7.8 plus or minus 0.5 in the Chinese. And this is Sandia, and this is Freiberg. Right, so anyway, this thing, so say 7.4 looks like that. He's saying that that's a sphere that's 7.8 nanometers, right? They're the same thing. Like it's the same thing. So what he has in this, and if you read the German paper, he talks about this. He says that they kind of do that. And in PinnyPan, because the persistence is so large, because it's got this amine, the side group, right, with the propeller on it, the isopropyl propeller. So he's got that polymer. So this is like a huge del minus, del plus. It's got partial charges. It's got like everything in it, right? So this is a gigantic group you can think of. Also, so this is hydrogen bonding. So it's got like a bunch of waters around it. So that's part of it also. It carries it with it. So this thing ends up being like really long. So it's like basically like 25 chemical mer units are making up a rod, right? It's gigantic. So you can imagine if you tether that to a sphere and hook that to the surface, and it's collapsed, and if that's the mechanism of collapse, is something like that, then it's going to pop off one by one. Like that's exactly what you see. Like one pops, one pops, one pops, and they're going to be basically spaced out at whatever 7.5 nanometer steps. Right, so whatever that one would be, so 23 or whatever. So I guess this is number of pops or whatever. So I mean that's kind of seems to be a more reasonable model of what's going on. It explains exactly where the 31 comes from. It's a persistence unit. I mean, it's a Kuhn unit. It's just like the base unit of the polymer. So why he didn't get that? I mean, he didn't look to see like what's going on, right? This is so anyway, let's see. In this thing, so this thing he's using an AFM. He's doing the AFM thing, like he's sticking the chains, and he has some I guess silanol coupling or something to the AFM tip. It's a quartz tip. Oh, sorry. This is the Freiberg. He's got a quartz tip. So silica silane, SiOH. And he's got some kind of amine silane bonding that goes on. He's got a thiol here, so it's like somehow this thing reacts with that, and he's got another bonding at the surface. It's the same molecule, but he's got isotactic and syndiotactic that he looks at. He made both of them. It's kind of a more complete study. It's in JAX. So JAX is, they're like nature science. And then you have like JAX. It's like next level after that, I guess. JAX and physical review letters. Proceeds of the National Academy. So it's like those are like the same level. This is a higher level in macromolecules. It's like 2 or 3 steps up. So it's a better journal. It's kind of better work. It looks like it's better, and that's probably why the other guy didn't publish. And so this guy does a GROMAC simulation, and he also does the AFM measurement. He does both, couples them together. So it's kind of a pretty complete, reasonable study. He doesn't see. I think he doesn't see the temperature transition. This is going through. I think it's at 30°C. So it'd be like right around 298 maybe, is where the transition to the coiled globule is. And I guess he doesn't look like he sees anything. I didn't really read this completely. See, he's got isotactic and syndiotactic and PEG. So he's comparing this flexible chain with the this kind of rigid chain. Kind of seeing how the differences go about in this thing. Anyway, this is a better paper, I think, in a lot of ways. The other thing our guy does is he takes it and he puts in salt. So he has like sodium sulfate, I think he puts in. Back at the end here, just says salt solution. It's in the, see, a lot of it is in here. And this is set up like sometimes in the old days you would submit a paper and you put the figures at the end and then the text at the front. So this supplemental set up like that. These days people just like, because you have in the old days you didn't have a word processor, so you did the graphics. This was typed on a typewriter, and then you put the graphics in by hand. You do hand layout of the things and everything. So anyway, that was the old days. Nowadays you don't have to do that. So there's no reason to stuff the figures at the end. It's stupid. Like it makes it unreadable. Like it's really almost unreadable. People had a lot more time to read stuff back then too. So anyway, so these are the figures. So he says like how he does this salt thing here. All the details are here about how to do the salt, I think. Magnetic calculation. It's up here somewhere. Anyway, I think it's sodium sulfate that he's using. So he adds it in, and somehow that makes the coil go through a collapse transition, So you can do it with temperature. So what's going on with this stuff? So you have and it asks you about basically there's the class notes on the coil globule. It asks you to just go through that, like kind of explain it or whatever. But coil globule is in the slides too. And then somewhere at the bottom. So you can kind of go through what I did. And then if that doesn't satisfy you, it's after this, right? And then it just goes coil globule. No, there's this junk. Coil globule is here. So it's like slide like 36. Starting with 36 and then goes on. And then Grossberg's book, it's chapter 9. It's a whole chapter that covers the same thing. 7, 8, 7, 9. So 8 short. Anyway, this is a whole chapter, just goes through the same thing. I mean, I basically took it from his thing because his thing's the most understandable. If you try to read the papers and things, it's kind of crazy. So his thing's pretty simple, but except he defines his own alpha, etc. Right? Like I went through in class. But so anyway, just kind of go through. There's like 3 or 4 steps. I don't think it's, it shouldn't be too bad to do that. Then that's one of the questions here, like explain the Grossberg, whatever. Then what? Yeah, B. So A is like, what is this magnetic thing? That's this paper, this thing, so, or whatever. That guy, a guide to, he kind of gives just gives a rough idea. And then Lou's nuances that the Grossberg is a single step, it like collapses, right? You go through that transition, it's a first order transition. And then PIM, it is first order, it's like boom. So you could argue it's second order, but anyway, so actually the Chinese guys would say it's second order because they show that slow rate of collapse, right? They have the quick rate. So there's 2 steps. There's one that's first order, which is actually pulling out individual persistence units. And the other is that slow thing. So they could argue it's second order, but I think everyone agrees it's first order more or less. And then the nuance is that he's got these single things that come out, which turns out, I think it's something to do with it, that the PIM has such a huge persistence length. 70 angstroms pretty big for a persistence length. So that's like 100,000 gram per mole polymer. Like a normal polymer, that's the rate of gyration of it, or maybe the end-to-end distance. So that's a huge persistence length. It's not microns, but it's pretty big. Normally, you're talking about 10 angstrom, or but you can see in the PEL it's something like 10. Anyway, so that's the nuance. He's got his 3-stage thing. So then this is about LCST. So it's just saying, like, how do you get what's the Floyd-Huggins equation? So let me just kind of go through that. We have a few minutes. Cam. So anyway, so I went through a little bit the Floyd-Huggins. We have like Helmholtz free energy, which can be like A, and everyone calls it F here. Right, and then by KT by the molecular weight. So this is a lattice model. So N is actually the number, not the molecular weight. It's a number of lattice sites. Like the number of lattice sites in a box, and you're going to put your polymer into the box, and you have the solvent in the other holes, right? So, and it's based on volume fraction. That's why it's Helmholtz. So you use volume, not Gibbs, right? If you want Gibbs, you add PV to it, right? So, and then I mean, and because it's Helmholtz, instead of enthalpy for Gibbs, it's internal energy, which equals H plus PV, or U is H plus PV, I think. So anyway, then you have the phi of the polymer, right? Then of the polymer, then ln of phi plus, this is a volume fraction. That's volume fraction. It's like 2 over N2. If this is solvent, that equals 1. And then ln of the solvent. And then you have this binary, so you have phi 1, phi 2 times this chi thing, which is the coordination number. So how many? So that's 6. Like that's 6 coordination at Cartesian. And then the delta E equals polymer plus solvent plus minus 2 times. Sorry, okay. By 2. So you have the polymer solvent. So both of those favor collapse. Those energies get larger, so that's an attractive potential. Then the E polymer solvent favors expulsion, like breaking apart, like solvation. So that's negative because it's an attractive potential from the van der Waals. Right? So then divide by 2, that gives you the average delta E. So chi is delta E divided by KT times Z, times that coordination number. Right, so that gives you the form B over T. Notice B is a different B than the second Viral coefficient. So maybe we'll call it B question mark or something. It's some box. It's basically a van der Waals A term, kind of. So that's B is van der Waals A. Right, so it's an attractive potential. And it's just enthalpic. Right, so if you have something like, oh, a bunch of water is going to come along and stick to the penny-pan side group, right? Well, that's organizational. That's going to lead to an entropy, not enthalpy, right? So that means you have to account for that with. So this is called combinatorial entropy. In other words, mix the boxes. It's like the marbles, shake the marbles up, you increase the combinatorial entropy, right? And this organization of water is called non-combinatorial entropy because they didn't have a word for what it is, I guess, you know. It's got, when you use the word non, it means you ran out of dictionary space or something. There's probably a better word for that. It's called non-combinatorial entropy. So that you account for by. So this is all going to be multiplied by T. So this thing doesn't have T and that thing does have T. Even on the equation, it doesn't have T and it does have T. Right. So anyway, this is entropy. It has T to get the free energy. ST. And then this is enthalpy. It's just H, or in this case, U, right? Because we don't have the PV part. So anyway, in order to get that, you add in just add in a term to this. So B over T plus A. So A is the non-combinatorial entropy. Right, so that allows you to account for this water sticking to it, which is a bad thing when it's mixed. A is positive. Right, the organization of the water is a bad thing for free energy. And when it's solvated, then it's going to have organized water. So you need to account for that with this A term. And then the B is B is negative. So because you're dividing by n, this term is essentially 0. So you need something to make it mix, and that's B. Okay, so when the temperature goes up, the negative thing drops, and the positive thing is more important, and then you get phase separation. There's a change. This is a change in free energy. So I didn't put a delta there. It's a change in free energy on mixing. So if it's positive, then it won't mix. It demixes. If it's negative, it mixes. Right? So to get that kind of chi thing rules everything, and you have A and B, and that gives you at high temperature it goes positive, so you get phase separation. That's an LCST. Temperature versus composition. So it's lower, so lower critical is the bottom. The other one, the normal one, is upper critical, where the entropy drives mixing, and this term is positive, right? It drives demixing, meaning that it actually is an attractive potential, just like in the van der Waals thing. So it drives phase separation like gas to liquid. All right, so then what happens so that gives us our normal LCST that we see in Pennypan. So what happens when you add sodium sulfate to that thing? So the sodium, so you're going to get the by screening. How do you spell it? B-E-B-Y-E screening. So you're going to get this length that's going to be like square root of the concentration. I think it's a KT somewhere in there too, but it's 1 over the square root of the concentration of the Na sodium ions, so, or the sulfate ions, or both. So it's basically you dump more salt in, this divide distance gets smaller, right? So that means the interactions disappear. So these things kind of fade away. Any kind of water, hydrogen bonding, everything gets washed out because you have no. So you have a plus and a minus, or del plus and del minus, but you have all these ions in between. They can't see each other. They don't know which direction. Something's happening, but it can't tell which way to go. The water is still like, but it feels like there's something there. It does feel that it's there, so it's a mean field, but it doesn't know, like, is it over there or over there? Can't tell. Where's your baby crying? I don't know. Somewhere in the room, I can kind of hear it. Yeah. So anyway, so that's the idea. Like you get crowded out by these charges, and you get that length gets smaller, then you can't see anymore, and then it basically becomes a non-charged polymer. Since this entropy term, the entropy term is bad, that should make it mix, but because it's upside down, it makes it demix kind of. So basically, this term A like disappears kind of. The organizational thing kind of goes away. And also the B also changes sign, I guess. I think that's what would happen here, because it's this organization that's causing the polymer to go into solution. So the enthalpy part changes, this thing just goes away. And the enthalpy part becomes positive. This term is 0, so it just phase separates as you add salt. You could probably explain it any other way you want to. This is kind of like the Chinese explanation, it's like based on conjecture. But that's the idea of this. I think the main idea is like you have these two terms. This term isn't affected. This term is essentially 0. And you have to make these two terms so it'll phase separate. And you could write an equation. Well, the A is going to go as 1 over the salt concentration or something like that, or some number minus the salt concentration. And the B is the opposite behavior, like B actually changes sign, so you need some term kind of like that, 1 minus or something, but so it has to change sign, go positive when you add salt. So you can imagine there'd be some functional form of that. Someone's probably proposed it. I don't know how much its value it's worth, but so it asks you to say like kind of what's going on here, right? So how could this be incorporated into the Fourier-Huygens? That's basically how, what term would be modified. There's room here for you to say whatever you want, as long as it ends up being that the change in free energy is positive when you add more salt. So you can say any way that you can get to that conclusion. Then from whatever you said, you could write an equation if you want, and then you you can predict the behavior. You need some data. All right, then changes can be in the 3 steps I already mentioned kind of what he's doing there. The 31 repeat units. So you can rip the guy apart if you want here. Like don't have any pity for the guy. Like just get used to being brutal about stuff. Like this, you don't say anything personal about him, but basically you could say they're completely misled, because they haven't even bothered to glance at the literature, which is replete with information about this huge persistence length, which is exactly the size of the thing they're proposing to be a bead. Right? I mean, don't be nice when you write about someone that screwed up in science, Being nice makes it that they can get away with it, and you can't, the idea is like, don't let anyone get away with anything if it isn't the truth, the absolute truth and whatever, so this is the only pure part of science, everything else is grabbing money, but you have to kind of be cruel about this kind of thing. But nothing, not personal, like, but basically like what he said doesn't make any sense. And he didn't look at the literature, which is bad. So doesn't result in a spherical globule. Explains 3 steps. How does he support it? So he supports it. The big problem is he's supporting it with just a force. You can't get structure from force, like you push up against the wall, you're blind. Oh, that wall's stuck there, but it could be an elephant or it could be anything, so you can't say it's a wall because they push against it and it doesn't move. It could be a rock. It could be a lot of things. I mean, so the force doesn't tell you anything at all about the structure. His conjecture is the whole thing. Like he's pulling on the thing, he sees it pop, pop, pop. Oh, those must be, and he looks at the Grossberg thing, he sees its little beads. It must be little beads, like the beads grow and shrink. So it makes sense, like they're gonna pop. Why it's 31, I don't care. So that's kind of his argument. So supporting it is just a force measurement, and that's not enough to really say. And he knew that, he even hinted that he knew that because he tried to get an AFM to show the little beads, like to show the 7.8 nanometer beads. And he got a micrograph that showed that, surprisingly. And then like basically what he is just probably artifacts, like what he got, right? So anyway, it's a good paper to go at it like that, I think, but adjacent, then he's proposed, then based off that cartoon, then he's proposed all this stuff, like 3 or 4 things about merging processes and the rate of the emergence process and how that's going to be influenced by salt versus temperature. He goes on and on about this emergence process that probably doesn't exist, right? So you can see, I mean, I hate it when it happens to me, because like it's easy to get down that track. Like you have a picture, you have a cartoon in your mind, it seems to agree with the data, and then you can make some predictions from it, and then it's a road you can get on, but basically when you see that happening, you have to be brutal to the person, to kind of most of the time anymore, no one's brutal. That's the problem with science these days. But so CGT has been proposed as a tool. And then he goes on to artificial muscles, which might have some merit to it, tuned by external stimuli. So at the end, this is kind of from the conclusion of the paper. He talks about the salt and how you could use that to make the muscle contract. Oops, sorry. No, what? Yeah, the conclusions. Where is it here? Yeah, he goes through this somewhere in here. He basically states this. If you read the conclusions, he's stating kind of where this is going, to artificial muscle. I can just search for muscle. So artificial muscles, there's 2 places where he says artificial. Oh, there's a paper in Nature about artificial muscles. Signed by which to mimic the mechanical properties of muscles. I can probably dig out that paper and put it up there because that's probably important to this thing in terms of like how you'd apply that. But anyway, so that it should be an easy homework. Like, it shouldn't be too hard to do, but You can never tell. It's a short paper. It isn't a long thing, right? I don't know, 10 page. I mean, it's pretty short. He doesn't say anything. Like he goes on and on about this. He goes on and on about these plots, like what?
Newspaper is just 9 pages, but then the other one that's about 33 or so.
Oh, with this thing, it's all pictures though.
Yeah, yes.
Yeah, all right.
Because you're comparing me with this.
I think you got to get used to reading something superficially, and then like when you need more, dig it deeper, right?
Oh,
Oh, this is where you can see. All right, so see, this is big so it's like the fluctuations, 1 over the fluctuations is the force, right? So he's got the force is small, he's got big fluctuations. Same with X and Y. Then the force is high, he's got small fluctuations. That's how he gets the force from the fluctuations. So actually he does this measurement and then he produces the bottom curve. But the bottom curve isn't the measurement, isn't done as an internal input. If he changes the temperature, the fluctuations get larger too. So you got to know what temperature it is to get the force. Kind of interesting. I mean, it's a nice little machine, right? I mean, pretty cool that they can do that. I mean, and what they did is take just the basic physics of the Brownian motion and get the force from that. It's nice how they did that. It's simple. It's really simple. And it seems to work. Like, I think it's a pretty cool thing. So it's kind of neat to look at that, and you can get information about the kind of basic information about things. But again, like if you don't know, you got to really see what people have done and kind of see what these numbers could be, like reasonably be. And if you get to a point where you got 31 and that's exactly the number, and you don't know why, like you'd think you would go back and look to see why, like, and then the obvious answer is it's a persistence length of the thing. These models, this is called a blob model, right? So you have this blob, you have a hierarchical structure, you have a huge thing, it's gonna be microns, and it's composed, and then you have the elemental thing, which is a Kuhn length. And in between, you have this blob idea, like things happen to it. So it can accommodate different stresses on the system, like temperature, force, concentration. And then as you do that, the thing can transition to different states. So that's a basic theme of polymer physics, like how things work, how complex. So if you have a molecule that's so large, then it can accommodate stuff in between the large size and the smallest size. And it's particularly just for polymers that do that, like that can accommodate, because it's so big, they have a hierarchical structure like that. Anyway, so this is a good, kind of a decent example of it. It's just that I think he messed up on it. And the German guys didn't. The Germans are smart, I mean, their school system is better than anyone else's. The people are just trained better. We should copy their school system if we could, but we won't. I mean, our school system is on just-in-time idea. Like, you don't need to learn anything until you absolutely need to know it, and then you can cram it in. That's our method. That's the American way, Basically, everything we do is like that. Like, the Germans, everything is kind of from their culture, it's compartmentalized, So they have, like, in other words, a German would never think to repair his own car. Like when I lived there for a little while, and I proposed, like, why don't you just change the air filter? I'm like, oh no, I'm not going to change the air filter, which is just like unscrew, pop it in, that's it, right? So because they have to take it to a guy, and they have a lot of respect for the car mechanic. It's like the guy is a professional, he wears a suit. I mean, really, it's different. Here it's just like a grunt, the cheapest one's the best one. There it's like, so everything's compartmentalized, it's different. And they respect each other. Like even the low end of society, they have a lot of respect for the people, like because they need them, because they don't want to do anything. Whereas we just take a wrench and put the air filter in, and that's it, and just forget about it. So it's different. Anyway, their training system though is that they know like everything. So when you work with a German that's been trained well, I mean, they're like incredible resource. They know like the whole thing. So anyway, that's why the German and the Chinese take after Americans, except in a like to another level, like an order of magnitude more. It's like they're just like get it out, get a paper in Nature. Boom, 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 you know, it's like they're kind of taking after us, but they've raised it up a level, I think. They're much more productive. The Germans aren't going to produce a lot of papers, but the ones they produce are going to be really excellent. So that's my impression. So Germans are good to work with if you can get to it. But anyway, so but they all like now a German will want to do a postdoc in the US so they can get their hands dirty. And then when they go back to Germany, they're valued higher because they think that they can actually cut corners or something, or they ignore rules, you know, or something. I don't know. So it's pretty strange. Like they don't, and they're trying to copy the US education system too, just like we tried to copy the Japanese system. And it doesn't work to copy someone else's system. It totally doesn't work. You got to have your own system. Yeah, that's the one that works for you. But we like if you tried to do the German here, probably people just wouldn't do it, you know. Anyway, why don't we quit there? So hopefully this isn't too bad. Email me if you get lost on this one, but I think it'll be all right. I think it's kind of interesting, you know.